Welcome to the deep dive. Today we're tackling something really crucial for building modern apps, concurrent collections and the task parallel library.
That's right. These are fundamental if you want software that can, juggle multiple things at once without grinding to a halt.
Exactly. If you've ever wondered how some apps just stay so responsive even when they're busy, well, this is often the secret sauce.
hmm It's all about managing tasks efficiently, whether that's user requests, data processing, or just keeping the UI smooth, making things faster, smarter.
So think of this session as our focused study guide on these topics. We've got some source material covering both concurrent collections and TPL.
And our mission really is to pull out the core ideas, the practical stuff you need to know.
Yeah, a clear, structured overview, like a cheat sheet almost, to get you up to speed on concurrency without drowning you in detail.
Right. We want to make these powerful tools feel a bit less intimidating, more approachable for your own work. We'll hit the key interfaces, the main classes, the patterns you'll actually use.
Okay, sounds good. Let's kick things off with concurrent collections then. The material starts with iProducer Consumer Collection T. What's the gist of this interface?
Okay, so this was foundational. Our producer consumer collection T is basically designed for situations where you have producers putting things in and consumers taking things out.
Like an assembly line.
Exactly like that, yeah?
Yeah.
It defines a contract for collections that are thread safe and optimized for that specific kind of interaction.
Yeah,
It's about having a shared space where multiple threads can safely pass data back and forth.
got it. And the main players derived from this are concurrent Qt, concurrent stack T, and concurrent bag T. Quick reminder, when would you reach for each one?
Sure. Concurrent QP is your classic FIFO first in, first out. Think of a waiting line.
Okay.
Concurrent stack T is LIFO last in, first out. Like stacking plates, you take the top one off first.
Right.
And concurrent bag T. That one's a bit different. It's often best when you have a mix of producers and consumers, and you don't strictly need that FIFO or LIFO order. Speed is prioritized, and duplicates are okay too.
Okay, that makes sense. Now, this base interface, iProducer Consumer Collection T, it has common methods like copy to, get enumerator to array, and then triad and tritake. What's the big deal about these?
The absolute critical thing is thread safety. Every single one of these is built to handle multiple threads messing with the collection at the same time without causing, chaos or data corruption.
So triad attempts to add, tritake attempts to remove.
Exactly. And they tell you if they actually succeeded, which is important in concurrent code. The others let you look at the contents, again, in a thread-safe way. And properties like count give you the size, while asynchronized and synchrone. Well, for the system.collections.concurrent types, asynchronized is usually false
Oh, why is that?
because they don't rely on a single simple lock for everything. They use more fine-grained, efficient synchronization methods internally. So synchron is typically null for them too. It's a different approach than just slapping a big lock on everything.
Interesting. Let's look at concurrent stack T as an example. The material shows it using a standard stack T inside, but with a locker object. Why the locker?
Right. That locker object is key to its basic thread safety. It uses the C# lock statement. When a thread wants to push something on or try pop something off, it has to acquire that lock first.
So only one thread can be pushing or popping at any given moment.
Precisely. It prevents two threads from tripping over each other while modifying the underlying stat data. Simple, but effective for guaranteeing safety.
And how does this concurrent stack T actually implement iProducer Consumer Collection T? I see tritake just calls tripop and triad calls push.
Yeah, it just maps its specific operations, push, try pop, to the more general interface methods, triad, tritake. This makes it usable wherever that interface is expected. And the way it implements iCollection, noting iSynchronize, is true here. And syncroot gives you the locker that just confirms it, uses this explicit locking strategy. Even copy-to uses the lock to get a consistent snapshot.
Okay. Now, blocking collection T sounds like it adds more control. What's its role?
Yeah, blocking collection T wraps one of those iProducer consumer collection T types, like a concurrent queue or concurrent stack, and adds blocking and bounding.
Blocking and bounding.
Right. Bounding means you can set a maximum capacity, an upper limit on the size. If you set a limit, producers trying to add items to a full collection will automatically wait. They block until there's space.
Ah, okay.
Producers can also signal, I'm done adding stuff, by calling complete adding. And on the other side, consumers will block if they try to take an item from an empty collection. They'll just wait until something shows up.
So they don't just get an error or a false return.
Exactly, they wait. And consumers can check the isCompleted property to see if the collection is empty, and the producers have called complete adding, so they know no more items will ever arrive.
So it's like flow control between threads?
Pretty much.
Mm.
It manages the interaction more tightly, prevents producers from overwhelming consumers or consumers from spinning pointlessly when there's no work. It's quite flexible, too. You can still do non-blocking triad and tritake if you want.
Mm,
And just be aware, while most methods are thread-safe, disposant.
good note. The material also talks about system.collections.concurrent generally, saying these collections are thread-safe and scalable without us needing to add our own locks. How do they pull that off?
They often use more sophisticated, lightweight synchronization techniques under the hood. Things like spin lock, spin wait, semaphore slim, countdown event.
Lightweight.
Yeah, instead of immediately putting a thread to sleep when it has to wait, which involves a costly context switch, these might use busy spinning for very short waits. The thread just loops very quickly, checking if the resource is free. If the wait is expected to be really short, this could be much faster than a full OS-level lock.
That sounds way better than those synchronized wrappers you can get from system.collections.generic. What's the problem with those again?
The big issue with the synchronized wrappers is that they put a single, coarse-grained lock around the entire collection. Anytime any thread wants to add, remove, or sometimes even just look at the collection, it has to acquire that one lock.
Creates bottleneck, right?
Exactly. It scales really poorly if you have many threads trying to access it. And worse, if you're trying to coordinate operations across multiple synchronized collections, you can easily break things because the locks aren't coordinated. You might update one but fail on the second, leaving your overall state inconsistent.
Okay, that makes sense. The material also distinguishes between pure and mixed producer-consumer scenarios. Why does that difference matter when picking a collection?
It matters because different collections are optimized for different access patterns. In a pure scenario, you have dedicated threads that only add items, and other dedicated threads that only remove them.
Right.
In a mixed scenario, the same thread might sometimes add and sometimes remove items. The performance characteristics can vary significantly. Concurrent bag T, for instance, often performs really well in those mixed scenarios, especially if the exact order items are processed isn't critical.
Let's dive into concurrent bag T then. Good for mixed use, order doesn't matter, duplicate's okay. What makes it fast in those situations?
It uses a clever trick involving thread local queues. Often, when a thread adds an item, it puts it into its own private little queue. And when it tries to take an item, it first looks in its own queue.
Ah, so it avoids contention with other threads.
A lot of the time, yes. Accessing its own local queue can often be done without any locking at all, which is a huge performance win when threads are both adding and taking. But a heads up, some of the extension methods or even methods from interfaces it implements might not be fully thread safe on concurrent BACT. Always check the docs. And while it's great for mixed, it might not be the absolute fastest in a strictly pure producer-consumer setup compared to, say, concurrent queue.
The example shows adding and taking ins using tasks. What's the key lesson there for our study guide?
It really just demonstrates the mechanics. You see multiple tasks concurrently throwing integers into the bag and other tasks simultaneously trying to pull them out. It also uses interlocked increment to safely update a shared counter, which is a common pattern you'll see alongside concurrent collections.
Okay. What about concurrent queueit and concurrent stack T? We mentioned they are often lock-free. What does that mean practically?
Lock-free means they avoid using traditional locks, like the lock keyword we saw in the simple concurrent stack example. Instead, they rely on very low-level atomic CPU operations, things like compare and swap.
CAS.
Compare and swap.
Yeah, it's an instruction that basically says, check if this memory location still contains value X. If it does, update it to value Y. Do this all as one indivisible step. The interlocked class in .NET provides access to these kinds of operations. It allows multiple threads to try to update the queue or stack simultaneously without blocking each other with locks. If two threads try at the exact same time, the CAS operation ensures only one succeeds cleanly and the other might just retry.
So it avoids the overhead of traditional locking.
Often, yes, especially under high contention where many threads are competing. It can lead to much better throughput, although it can sometimes involve a bit of spinning if there are conflicts.
Got it. And the key methods to remember for these. For concurrent queue. For concurrent queue, it's enqueue to add, try to queue to remove, and try peek to look without removing.
And concurrent stack.
Push to add, try pop to remove, try peek to look, And importantly, it also has try-push range and try-pop range for adding or removing multiple items at once, which can be a significant performance boost, especially in those mixed scenarios.
The performance comparisons between the concurrent versions and locked regular versions are interesting. What's the summary?
It's nuanced. For a concurrent queue versus a locked queue in a pure producer-consumer setup with very fast operations, concurrent queue might have a slight edge. But surprisingly, in mixed scenarios with fast operations, sometimes the simple locked queue scales better. Yeah. For concurrent stack versus a lock stack in pure scenarios, performance is often similar. A lock stack might even pull ahead slightly with lots of threads sometimes, maybe due to contention patterns. But concurrent stack often wins in mixed scenarios because of those push range, pop range methods. The big takeaway is, there's no single always faster answer. It really depends on your specific workload. Pure versus mixed, how long each operation takes, how many threads. Benchmarking your actual scenario is often key.
Good advice. Last one in this section, concurrent dictionary T-key, T-value. How does it manage thread safety?
Concurrent dictionary is optimized for concurrent reads and writes. Reads are generally lock-free, which makes lookups very fast, even with many threads reading.
And writes.
For writes, adds, updates, removals, it uses fine-grained locking. Instead of locking the whole dictionary, it only locks the specific small segment or bucket where the key resides. This allows many writes to happen concurrently, as long as they target different parts of the dictionary.
So much better concurrency than just locking a regular dictionary.
Absolutely. Now, not all methods are atomic in the sense of a single indivisible operation, but the core ones, like try-add, try-update, add-or-update, get-or-add, are atomic, which is crucial. The exception is if you use a delegate within a door update or getter add to calculate the value, the delegate execution itself isn't part of the atomic dictionary operation.
So when should we definitely use concurrent dictionary over a locked dictionary?
The sweet spot is when you have multiple threads, frequently adding and updating items concurrently. You'll see big benefits there. You might see some gains even with lots of updates and fewer reads. But if your dictionary is mostly read from and writes are rare, a regular dictionary might actually be slightly faster because it doesn't have the overhead of even the fine-grained locking mechanism.
Okay, that's a really helpful tour of concurrent collections. Let's switch gears now to the task parallel library, the TPL. What's the big picture here? Why is it so important?
The TPL is basically a set of APIs in .NET designed to make it much easier to add parallelism and concurrency to your applications. It abstracts away a lot of the raw thread management.
How so?
Well, it handles things like dynamically figuring out how many threads to use based on your system's cores, breaking down work into smaller pieces, partitioning, scheduling those pieces onto the thread pool, providing ways to cancel operations, and managing the state of tasks. It lets you focus more on the what needs to be done concurrently rather than the low-level how of managing threads.
Where does the TPL typically shine? What kind of scenarios?
Oh, lots of places. Keeping your UI responsive is a big one, running slow operations in the background. On servers, handling many incoming requests at the same time efficiently. Speeding up CPU-intensive calculations by splitting the work across cores. Even more advanced stuff like speculative execution. It's pretty versatile.
The material differentiates between data parallelism and task parallelism. Can you break that down for us?
Sure. Data parallelism is about doing the same operation on many pieces of data concurrently. Think applying a filter to 1,000 images. The operation is the same. The data differs. The TPL helps partition the data, the images, and processes the chunks in parallel.
Okay, and task parallelism.
Task parallelism is about running different, potentially independent tasks concurrently. Maybe one task fetches data, another processes it, a third updates the database. Here, it's the distinct tasks themselves running in parallel, not necessarily the same operation on different data. Data parallelism is often great for scaling computationally heavy work on multi-core machines. Task parallelism gives you more flexibility to orchestrate complex workflows with different steps happening at the same time.
Let's focus on data parallelism first. We see the familiar for and for each loops, and then parallel for and parallel for each. How do these parallel versions work their magic?
Essentially parallel. For and parallel. For each take the iterations of your loop and automatically distribute them across multiple threads managed by the thread pool. You give the loop bounds, or the collection, and a delegate representing the body of the loop the code to run for each item or index. The TPL then handles the partitioning and scheduling to run those loop bodies concurrently.
The idea of thread local variables comes up with parallel for T. What problem are they solving in a parallel loop?
Right. Imagine you're summing up values in a huge array using a parallel loop. If multiple threads just try to increment a single shared total variable, you'll get race conditions and incorrect results.
Because they'll overwrite each other's updates.
Exactly. Thread local variables solve this. With parallel 4T, you can declare a variable that exists separately for each thread running the loop. Each thread accumulates its own subtotal in its local variable. You provide an initialization function, local init, that runs once per thread, the main loop body that updates the thread's local variable, and then a finalization function, local finally. This last one runs once per thread after it's done all its iterations, and it's where you safely combine the thread's subtotal into the final overall total, usually using a lock or interlocked operation.
Okay, so it avoids the constant contention on the shared variable during the loop itself.
Precisely. And then there are partition local variables for parallel for each. Similar idea, but the scope is tied to a partition of the data rather than strictly a thread. One thread might process multiple partitions. It serves a similar purpose of isolating intermediate state.
Parallel aggregation is mentioned too, emphasizing that the operation needs to be commutative. Why is that important?
Commutative means the order doesn't matter, like addition. 2 plus 3 is the same as 3 plus 2. When you're combining partial results from different threads in a parallel operation, you can't guarantee the order they'll be combined in. If your operation isn't commutative, like subtraction 5-3 isn't 3-5, combining partial results in an arbitrary order will give you the wrong answer. So for parallel aggregation to work correctly, the combining step needs to yield the same result regardless of order.
Makes sense. We also get parallel loop result back from these loops with is completed and lowest break iteration. What do these tell us?
Is completed is straightforward. True if the loop ran through all its intended iterations without stopping early, false otherwise. Lowest break iteration is useful if you use parallel loop state break inside your loop. It tells you the index of the earliest iteration that requested the break, helps you know how far it got before decide to stop.
And if we need more control, there's parallel options. What can we tweak there?
Parallel options lets you fine-tune things. Max degree of parallelism lets you limit how many threads the TPL uses. Maybe you don't want it to swamp your CPU. You can pass in a cancellation token to enable cooperative cancellation of the loop. And you can even provide a custom task scheduler if you need really specific control over how the loop's work is scheduled.
Speaking of stopping, we have parallel loop state break and parallel loop state stop. What's the difference? And any gotchas?
They both stop the loop early. Break is softer. It signals that iterations with an index higher than the current one shouldn't start, but it tries to let any currently running lower index iterations finish. Stop is more abrupt. It tries to halt all execution as soon as possible.
So stop is more forceful.
Yes. The main gotcha is you can't use both in the same loop. Also, because things run in parallel, even with break, some iterations after the breaking one might have already completed, and some before it might not have even started yet. It's not a perfectly clean cutoff at the break index.
The examples show using break and also cancellation tokens. What are the key takeaways from those patterns?
The examples really just show the standard way to do it. Inside the loop body delegate, you get access to a parallel loop state object. You can call state.break or state.stop based on some condition. For cancellation, it's the standard .NET pattern. Create a cancellation token source, get its token, pass that token into parallel options. Inside your loop body, you periodically check token, is cancellation requested or call token. Throw if cancellation requested. If you call the latter, it throws an operation canceled exception if cancellation was signaled, which you then need to catch outside the parallel for each call.
And shared state inside these loops still need locks.
Absolutely, yes. If multiple iterations might read or write the same shared variable or resource, you must protect that access with locks or other synchronization mechanisms, interlocked, etc., just like in any multi-threaded code. The TPL doesn't magically make shared state safe. It just runs your code in parallel. You're still responsible for protecting shared data.
How about exceptions within the loop iterations? How does the TPL handle those?
If an unhandled exception occurs in any of the loop bodies, the TPL catches it. It doesn't immediately stop everything, though. It usually lets currently running iterations finish, but prevents new ones from starting. It collects all exceptions thrown by any iteration into a single aggregate exception.
Ah, so you catch that one exception type outside the loop?
Exactly. You wrap your parallel for each call in a try-catch block that catches aggregate exception. Then you can iterate through its inner exceptions property to see all the individual exceptions that occurred during the parallel execution and handle them appropriately. If you don't catch it, the aggregate exception propagates up and can crash your app.
Data partitioning with the partitioner class is mentioned for loops with small bodies. Why does that help?
When the work inside each loop iteration is super fast, the overhead of the TPL managing each tiny iteration, individually scheduling it, synchronizing can actually outweigh the benefit of parallelism. It might even be slower than a regular sequential loop.
So you process bigger chunks.
Right. The partitioner lets you define how to break the source data into larger, more meaningful chunks. You create a partitioner,
Hmm?
like partitioner, create for ranges or collections, and then parallel. For each can process one chunk per task. This reduces the per item overhead and can significantly improve performance for those fine-grained workloads.
Good tip. What are the main pitfalls to watch out for with data parallelism?
Okay, key ones. Don't parallelize loops with very few iterations or super fast bodies. The overhead might kill performance. Always protect shared state accesses with locks to avoid race conditions. Be wary of hidden dependencies between iterations. If iteration n needs the result of iteration n1, simple parallelization won't work. Avoid excessive nesting of parallel loops, usually just parallelize the outer loop, and be careful calling non-thread safe methods from inside the parallel loop body, and watch out for thread affinity issues, especially in UI apps.
Got it. Let's shift to parallel LANQ, or PLANQ.
Right.
How does this fit in with regular LANQ?
PLNQ is essentially LINQ to objects turbocharged for parallelism. You take a standard LANQ query operating on an in-memory collection, and you just add AskParallel somewhere near the start of the query chain.
That's just add as parallel.
Well, pretty much. PLINQ then takes over. It analyzes the query and the data source. If it thinks parallel execution will likely be faster, it automatically partitions the source data and executes the LINQ operators, like where, select, order B, across multiple threads. Like regular LINQ, execution is usually deferred until you actually enumerate the results, example with for or total list.
So it tries to be smart about when to parallelize.
Exactly. It has heuristics. If the query is very simple or the data source is tiny, it might decide the overhead of parallelization isn't worth it and just run the query sequentially, even if you added as parallel. It aims for performance improvement, not just parallelism for its own sake.
What kinds of queries benefit most, and which ones maybe not so much?
Computationally expensive queries are prime candidates. If your select or where clause involves a lot of calculation per item, PLINQ can give you a nice speed up. On the flip side, queries that do very little work per item, a simple where on an integer, might actually get slower due to the overhead. Also, operations that inherently require coordination or ordering, like order B, group B, join, take, can sometimes limit the benefits or add overhead in the parallel version, because PLINQ has to do extra work to manage the order or combine results correctly.
What other performance factors should we consider with PLANQ?
Several things. The overall cost of the operations, as we said. The number and type of operators, some are more parallel-friendly than others. How you consume the results, forcing execution with toList, or toArray, triggers a merge phase, where results from worker threads are combined, which has its own cost. PLINQ actually offers different merge options, like buffering or streaming, that can affect responsiveness and throughput. And finally, how the data gets partitioned. If the work per item varies wildly, some threads might finish much earlier than others, leading to suboptimal load balancing. You can sometimes provide custom partitioners here too.
The examples show using ace-ordered and mixing-ordered. What's that about?
By default, PLINQ doesn't guarantee preserving the original order of elements because doing so often adds overhead. If you need the output sequence to be in the same order as the input, you add ace-ordered.
But that might slow it down.
It can, yes. The other example shows a clever trick. Maybe you need ordering for an initial part of the query, like take 10 after ordering, but then you have a very expensive operation like a join, where order doesn't matter anymore. You can use as-ordered for the first part, then insert as unordered before the expensive join to tell PLINQ, okay, you could disregard order now for better parallel performance during this join, and then maybe add as ordered again at the very end if the final result needs sorting. It's about strategically controlling the ordering constraint.
Okay, that covers data parallelism pretty well. Let's move into task parallelism more directly. The material starts contrasting synchronous and asynchronous operations. Quick refresher.
Sure. Synchronous means you call a method, your code waits, blocks, right there until the method finishes and returns. Asynchronous means you call a method, it starts the work, but it returns control to your code almost immediately before the work is actually done. The work continues in the background, your code is free to do other things, it's non-blocking.
And why is asynchronous programming so important, especially for things like I/O or long calculations?
Huge benefits. It often simplifies threading code because the framework handles a lot of it. For I/O-bound stuff, network requests, file access, it massively improves scalability because you aren't tying up threads just waiting idly for responses. And crucially for UI apps, it keeps the user interface responsive. The UI thread doesn't freeze while waiting for a background operation to complete.
The recommended approach now is the task-based asynchronous pattern, or TT. What did it replace and what makes it the standard?
Yeah, TT is the modern way in .NET. It largely replaced the older EAP, event-based asynchronous pattern, and APM, asynchronous programming model. TTP is built around the task and task result types. It provides a much cleaner, more composable model. It uses futures and continuations behind the scenes, and usually relies on a single method, often ending in async, to represent the whole async operation.
We see the comparison of read versus read async. How does read async returning a task int change how we use it?
That taskInt represents the future result of the read operation. Instead of blocking until the read completes, read async returns this task immediately. You can then use the await keyword on that task. Await pauses your method's execution without blocking the thread and arranges for it to resume automatically when the task, the read operation, eventually completes. This is way simpler than the older patterns involving callbacks or begin-end methods.
Why is using task preferred over directly using thread objects for this stuff?
Task is a much higher level abstraction. Creating and managing raw thread objects is complex and error-prone. Tasks integrate seamlessly with the TPL's thread pool management, cancellation framework, exception handling, and continuations, chaining operations together. Getting results back from a background operation is trivial with task result. It just provides a much richer and more robust model for asynchronous programming.
The terms future, promise, and continuation come up. How do they map to .NET constructs?
Think of it like this. A task result is a future. It's a placeholder for a result that will arrive later. A task completion source result acts like a promise. It's the object you use to create that task, future, and later fulfill it by setting its result or exception. And a continuation is simply code that's scheduled to run when a task, the antecedent, completes. The await keyword implicitly creates continuations, or you can use methods like continue with explicitly. The examples show sequential versus parallel, using parallel.invoke and task.factory.startNew. What's the difference in how they achieve parallelism? Parallel. Invoke is a simple way to just run a few separate actions concurrently. You give it the delegates, and the TPL runs them in parallel, waiting for all to finish. Task factory start new, or the more common task run, explicitly creates task objects for your actions. This gives you more control, you get the task objects back, you can wait on them individually, chain continuations, etc. The example uses task, wait all, to explicitly block the main thread until both tasks created with start new are done.
We also see task completion source and task delay. What are these illustrating?
The task completion source example shows the promise future pattern directly. You create the source, promise, get its task, future, and then sometime later, you manually complete the task by calling setResult on the source. This is useful when you're wrapping older async patterns or operations based on events. The task, delay examples show how to create a task that simply completes after a time interval. Using getAwaiter, on completed or to continue with, demonstrates two ways to attach a continuation code that runs automatically after the delay task finishes.
The prime number continuation example seems more involved. What's the core idea there?
It shows chaining. You start an asynchronous operation, prime number task. Then you attach a continuation that will only run after that initial task finishes. The continuation gets access to the result of the first task, antecedent result, and can then do something with it, like printing the result. It demonstrates how to sequence asynchronous operations, where one depends on the output of the previous one, all without blocking.
What about long-running tasks? How should we handle those differently?
The default thread pool is optimized for relatively short, compute-bound work. If you have a task that's going to run for a long time, or especially one that might block, like waiting on I/O indefinitely, just throwing it onto the thread pool isn't ideal. It can lead to thread pool starvation.
So what's the alternative?
You can use task.run or task.factory.no with the task creation options long-running flag. This hints to the scheduler that it might be better to dedicate a separate thread to this task outside the main pool. For multiple blocking long-running tasks, especially I/O-bound ones, using task completion sourced and the async await pattern is often best. For CPU-bound ones, a producer-consumer queue pattern might be more scalable.
The task status enum lists states like running, ran to completion, faulted, canceled. Are these useful to monitor?
They can be, yeah, especially for debugging or building more complex coordination logic. Knowing if a task completed successfully, renda completion, failed with an exception, faulted, or was canceled can be important. Waiting to run and running tell you about its progress.
What are the essential task operations we should know? Creation, waiting, getting results.
For creation, task, run is common now, or task factory.start new. For waiting, though prefer await in async code, you have task, wait, task at dot wait all.
Ah,
For monitoring, check task statsy waitay. For getting results from test result, use task. Result, again, this blocks, so prefer await task in async methods.
cancellation is crucial. How does the TPL handle canceling tasks?
It uses a cooperative cancellation model based on cancellation token source and cancellation token. You create a cancellation token source, you get its token property, which is a cancellation token. You pass this token into the method that starts your asynchronous operation, e.g. task. Run takes it as an argument.
And then the task itself needs to check the token.
Yes, that's the cooperative part. The code running inside the task needs to periodically check the token's is cancellation requested property. If it's true, the task should clean up and exit gracefully, often by throwing an operation canceled exception. Alternatively, it can just call token, throw if cancellation requested, which does the check and throws the exception automatically if cancellation was requested.
And how do we handle that operation canceled exception?
You catch it like any other exception, typically using a try-catch block around the await task call or wherever the exception might propagate from. You specifically catch operation canceled exception. You might log it, or just treat it as a normal way for the operation to terminate early. A finally block is still useful for cleanup that needs to happen, whether the task completed, failed, or was canceled. Remember, the task has to check the token. Just calling cancel on the source doesn't magically stop the running code.
What common mistakes do people make with task parallelism?
A big one is closures capturing loop variables incorrectly. If you start tasks inside a loop, and the task delegate captures the loop variable, all tasks might end up seeing the final value of the variable, not the value it had when the task was created. Using a local copy inside the loop fixes this. Another is disposing of resources, like streams or database connections, that an asynchronous task is still using. The task might start, the outer method continues, disposes the resource, and then the task fails when it tries to use the disposed object.
The material mentions task scheduling, global versus decentralized, work stealing. Can you give us the quick version?
Okay, so the TPL needs to decide which thread runs which task. A simple global queue for all tasks is easy to understand, but bad for performance due to synchronization contention. The TPL uses a smarter decentralized approach. Each thread pool thread has its own local queue, plus there's still a shared global queue.
Local queues are faster.
Yes, threads can usually grab work from their own local queue very quickly without locking, often using LIFO, last in, first out. If a thread's local queue is empty, it looks at the global queue, often FIFO, first in, first out. If that's also empty, it tries work stealing.
Stealing work.
Yeah, it looks the local queue of another thread and tries to steal a task from there, often taking from the bottom, FIFO style, to reduce conflict with the owner's thread taking from the top, LIFO style. This helps keep all threads busy and balances the workload dynamically.
The futures application scenario talks about linking operations, some parallel, some sequential. How does TPL help model this?
You represent each step as a task. If steps F1 and F2 can run in parallel after step A completes, you start them concurrently. If step F3 needs the result of C, you typically await C before starting F3 or access C result carefully. If F4 needs results from both B, the result of F1, and D, the result of F3, you'd wait for both F1 and F3 to complete before starting F4. Tasks naturally model these dependencies.
And the continuation scenario sounds similar, but emphasizes avoiding blocking.
Right. Instead of blocking using B result or D result, you'd use continuations. You could use task, when all BD, to get a new task that completes only when both B and D are done. Then you can await that task or attach another continuation using .continueWith to run F4 once both prerequisites are met. It achieves the same workflow as futures, but in a potentially more non-blocking way.
The parallel sum using continuations example looks complex. What's the core idea it's showing?
It's demonstrating a divide and conquer approach using tasks and continuations. It breaks the array into smaller chunks. Tasks compute sums for these chunks. Then, continuations are set up to take the results of pairs of these tasks, sum them, and produce a new intermediate result task. This continues up a tree structure until a single task at the top holds the final sum. It's about propagating results through a chain or tree of asynchronous operations using continuations. The semaphore slim there just limits the degree of parallelism.
And the benchmarks comparing that with other methods.
They suggest that for that specific problem, the continuation-based approach might not always be the absolute fastest compared to simpler thread pool or countdown event methods, but it can be a more expressive way to structure certain kinds of dependent parallel computations. Performance depends heavily on the specifics.
Okay, last TPL topic. Pipelines. What are they for?
Pipelines are great for processing a sequence of items through multiple stages, where each stage does a piece of the work. Think of an assembly line again. Item goes through stage 1, then stage 2, then stage 3. The key is that stage 1 can be working on item n plus 1, while stage 2 is working on item n, and stage 3 on item n1, all concurrently.
Improving overall throughput.
Exactly. The TPL helps build these using blocking collection T as the buffer or conveyor belt between stages. Stage 1, a producer task, does its work and adds the result to a blocking collection. Stage 2, a consumer producer task, takes items from that collection, processes them, and adds its result to the next blocking collection, and so on. Each stage runs as a task.
The image pipeline example clarifies this. How do you handle exceptions gracefully in a pipeline like that?
It requires coordination. A good pattern is using linked cancellation tokens via cancellation token source. Create link token source. You link the tokens for all stages. If any stage hits an unhandled exception, it should first signal cancellation on the linked source, which notifies all other stages to stop, and then perhaps rethrow the exception.
So one failure can cleanly shut down the whole pipeline.
That's the goal. Each stage needs its own try-catch. And importantly, when a stage calls add on its output blocking collection, it should pass the cancellation token. Why? Because if a downstream stage has already canceled and stopped taking items, the add call could block forever, causing a deadlock if you don't pass the token.
Good point. Any key performance considerations for pipelines?
Ideally, you want the time taken by each stage to be roughly equal for maximum throughput. If one stage is much slower, it becomes a bottleneck. You might need to parallelize that specific stage internally. Long pipelines can potentially lead to thread pool issues or deadlocks if buffers fill up, and robust exception handling and cancellation are critical for stability.
Wow, okay. We've covered a ton on concurrent collections and TPL. Let's move to the final piece. Async and await. The material says these made async programming mainstream. Why such a big impact?
Because they made it so much easier to write and read asynchronous code. Before async await, writing non-blocking code often involved complex callbacks, go back hell, or intricate state machines. Async await lets you write asynchronous code that looks almost like synchronous code, using familiar control flow structures like try-catch and loops. The compiler does the hard work of transforming it into a state machine behind the scenes.
And modern frameworks rely on it heavily.
Oh, absolutely. ASP.NET Core, for instance, is fundamentally built around async operations. If you're doing modern .NET development, especially anything involving I/O, you pretty much have to use async await. And the pattern tends to spread. If you call an async method, your method usually needs to become async too, so you wait it.
Let's break down the keywords, the async modifier first.
Async is just a marker you put on a method signature. It tells the compiler this method might contain await expressions. It enables the await keyword within that method. An async method must return void, task, or task result. It can't have ref or out parameters.
And await, what does it actually do?
Await is where the magic happens. You put it before a call that returns an awaitable type, usually a task or task result. When execution hits await, if the task hasn't completed yet, await does two things. First, it arranges for the rest of the method to run as a continuation when the task does complete. Second, it immediately returns control to the caller of the async method.
So the current thread isn't blocked.
Exactly. The thread is freed up to do other work, like keeping the UI responsive. When the awaited task finishes, the continuation of the rest of your method gets scheduled to run, potentially on a different thread depending on the context. If a method marked async doesn't actually contain any await keywords, it just runs synchronously, but still wraps its return value in a task.
The example with trace, compute something, and compute something async using task, run, illustrates this. Can you walk through the thread IDs in the output?
Sure. Main starts usually on thread 1, the main app thread. It calls compute something async. Inside that, task, run, queues the compute something work onto a thread pool thread, say thread 4. Compute something async immediately returns a task to main. Main continues, maybe prints something. Meanwhile, thread 4 starts executing compute something, which blocks that thread for 2 seconds. After 2 seconds, thread 4 finishes compute something, completing the task returned by task. Run. Back in main, the await t line was reached earlier. Since the task wasn't complete then, main yielded. Now that the task is complete, the rest of main, the code after await t, gets scheduled to run. It might run on thread 4 or another thread pool thread, or potentially back on thread 1 if there's a synchronization context. The key is that thread 1 wasn't blocked during the 2-second wait.
Okay, that clarifies the non-blocking aspect.
Yep.
Now, why the strong warning against async void methods?
Async void is problematic, primarily because the caller has no way to know when the operation completes. It returns void, not task. This means you can't await it. You can't easily compose it with other async operations. And crucially, exception handling is a nightmare. An unhandled exception thrown out of an async void method usually crashes the process directly because there's no task object to capture it.
So basically, never use it.
Pretty much. Stick to async task or async task result. The only generally accepted use case for async void is for top-level event handlers, like button-click handlers in WinForms WPF, because the event signature requires void. Even then, you should usually have the async void handler immediately call and await an async task method containing the actual logic.
Synchronization contexts are mentioned with await. What are they and why do they matter for UI apps?
A synchronization context is basically an object that represents a specific environment for running code, like the UI thread in a WinForms or WPF app, or an ASP.NET request context. When you await a task, the runtime captures the current synchronization context, if one exists. By default, when the awaited task completes, the continuation, the rest of your method, is posted back to that captured context.
So in a UI app, it automatically gets back onto the UI thread.
Yes. That's why you can safely update UI controls after and wait in an event handler. The context ensures you're back on the correct thread. However, sometimes, especially in library code that doesn't interact with the UI, you don't want or need to force the continuation back onto the original context. Forcing it back can sometimes cause deadlocks or performance issues.
And that's where configure await false comes in.
Exactly. If you write await some task.configure await false, you're telling the runtime, I don't care about the original context, just run the continuation wherever is convenient, usually thread pool thread. This is often recommended for library code to make it more robust and performant when consumed by different types of applications.
The material stresses using await instead of blocking calls like task, wait, or result inside async methods. Why is mixing them so bad?
It's a recipe for deadlocks, especially with synchronization context. Imagine this. Your UI event handler on the UI thread calls an async method. Inside that method, you call some other async task, result. This blocks the UI thread until some other async task completes. But what if some other async task, when it finishes, needs to post its continuation back to UI thread's synchronization context? It can't, because the UI thread is blocked waiting for result, deadlock.
The thread is waiting for itself, essentially.
Precisely. Using await throughout avoids this by never synchronously blocking the thread that might be needed by the continuation. So the rule is, inside an async method, prefer await, await task, when any, await task, when all, avoid wait, wait all, and result.
We see examples for I/O-bound and CPU-bound async operations. What's the pattern for each?
For I/O-bound, like network calls with the HTTP client getString async, you just await the naturally asynchronous method provided by the library. The thread is released during the wait. For CPU-bound work, heavy calculations, that you want to run without blocking the caller, like the UI thread, the pattern is to wrap the synchronous CPU work in task, run, and then await the task returned by task. Run. This pushes the work onto a thread pool thread.
Oh, okay. And canceling after a timeout using cancellation token source and task, when any. How does that work?
It's a neat trick. You start your main async operation, do-work async, and pass it a cancellation token. You also create a task, delay for your timeout duration, passing it the same cancellation token. Then you use await task, any work task, delay task. This awaits whichever task finishes first. If delay task finishes first, it means your work task timed out. You can then signal cancellation to work task using the cancellation token source and handle the timeout. If work task finishes first, you know it completed within the time limit.
Clever. How about reporting progress from an async task?
The standard way is using the iProgressT interface and the ProgressT class. Your UI cone creates a ProgressT instance, often providing a lambda to its constructor that updates a progress bar or label. This lambda will automatically run on the UI thread thanks to the synchronization context captured when ProgressT was created. You pass this iProgressT object to your async method. Inside the async method, whenever it makes progress, it calls progress. Report, new value. This triggers the lambda back on the UI thread, updating the UI safely.
The summary table comparing await versus blocking alternatives seems really useful for a study guide. What's the absolute core message?
Use async await for I/O. Use task. Run plus async await for CPU-bound work you want to offload. Use task T to represent the work. Async enables waits without blocking. And crucially, inside async code, always prefer the await-based ways of waiting. Await task, when any node a task, when all, await task delay, over the synchronous blocking equivalents. Wait result, wait any, wait all, thread sleep.
Any other final tips or guidelines mentioned for async await?
Yeah, try to keep async methods relatively small and focused, minimize shared mutable state if possible, and consider using value task D in performance-critical scenarios where the async method might often complete synchronously, as it can help reduce memory allocations compared to task T. The material also points to further reading on the underlying state machines if you want to go really deep.
This has been incredibly thorough. We've really dug into concurrent collections, the whole task parallel library, and async await. It feels like a really solid overview, perfect for that study guide goal.
I think so too. We tried to hit the essential concepts, the patterns, the gotchas. The key is understanding the different tools and when to apply them. Hopefully this gives everyone a much stronger foundation for tackling concurrency in their .NET projects.
Definitely. And remember, you can always revisit parts of this discussion if you're working on a specific area.
Absolutely. Practice and applying these concepts is where the real learning happens.
So a final thought to leave you with. Now that you have a better handle on these concurrency tools, how might that change how you approach designing software or thinking about performance? Can you spot opportunities in your own work or maybe real-world problems you see differently now through this lens of concurrency, something to mull over? Thanks for joining us on this deep dive.